So before we get started, a quick look at the Daddy Pig YouTube channel. This is where we keep the recordings of the webinars, also other little videos as well, which may be of interest. So if you look under the playlists, you will find CPD webinars for structural engineers, and that's where we've got the previous 30 webinars actually recorded and edited. I've extracted some of the Mathcad calculations so to have short introductions to Mathcad in the Mathcad for structural engineers, and other issues, introductions to software, for example, come under the Piglet files. So if you're watching on YouTube, don't forget to subscribe to the channel, give me a like or a comment, and share the show with your friends. Well, welcome to another CPD seminar for structural engineers. This time we'll be talking about the design of anchors in concrete, and we've particularly focused on holding down bolts that are cast into concrete footings, although we look at other things as well. The procedure generally follows our own code NZS 3101, and that's the one for concrete building design. Yes, it's another seminar asking what does this spreadsheet do, because there is a Redco spreadsheet for this, and hopefully we'll expand it in the Mathcad version, basically longhand. So the scope of today's seminar will look at the types of anchors, the design criteria that you'll need when designing those anchors, a quick word on group capacity versus individual capacity, quick look at the Hilti Profis software and the Rang iExpert software, a quick look at the Redco spreadsheet, a discussion on the failure mechanisms, and then a deep dive into the Mathcad example. Then we'll pause for questions, and I'll take your questions and answers and comments after that. So beginning with types of anchors, they split roughly into two types. Cast in, as you can imagine, these are anchors or bolts and holding down fixings which are cast into the concrete as you make the concrete. The alternative is post-installed anchors. Now, often contractors prefer these because the cast-in anchors, you need to have some accuracy as to locate the bolts in the right place. Particularly if it's foundations, you don't really have a great deal of room to play around with, whereas the post-installed anchors, you can put exactly where you want. And the post-installed anchors split into mechanical or chemical. So the mechanical anchors are looking at expanding bolts usually, or even undercut anchors. So their strength comes from their mechanical anchoring. The alternative is the chemical anchor, which relies on the adhesive between the steel and the concrete. And NZS 3101 has this clause in it that basically says post-installed anchors need to be pre-qualified using the testing stipulating in ETAG 001 and EOTA TRO 45. Now these were both issued around the 2013 mark and have kind of been superseded by the Eurocode now, but they are still in use and will still refer to ETAG or ETA design. So typical implementations are from Hilti and RAM. Other manufacturers produce them, including Rollplug and Fisher and Python, which we'll have a mention of later. The design criteria for anchors, well, the first obvious thing is how deep is the anchor? It's the anchor embedment, how wide is the anchor? So your anchor diameter and the anchor spacing. So that's all down to do with the physical properties of the anchor. The more subtle criteria is how close are you to the edge? So NZ 3101 gives you these diagrams, and you're talking about edge distances C1 and C2, as well as the spacing between the bolts of S1 and S2, and these can be your governing criteria. Also, to a lesser extent, concrete strength and the base reinforcement. and confirming whether you're cracked or uncracked concrete, which we will discuss later. For eccentric loading or offset bolts, prying can become an issue as it increases the load in your anchors. Quick word on group versus individual capacity. Just because you have an individual capacity of one bolt, 10 kilonewtons, don't assume that 6 bolts together in a group gives you a capacity of 60 kilonewtons. It's not that simple because there's an interaction between the two, and the amount of concrete you're using is shared among the anchors. And a reference back to CPD seminar number 25, we looked at in more detail structural steel connection design to 3404. Today we're looking at the concrete side of things. So when you're looking at a holding down bolt system and a base plate in a steel frame structure attached to a concrete foundation, you've got to look at NZS 3404 as well as NZS 3101. And I did a little talk on the Bentley RAM connection software, and that's one of my Piglet files you'll find on the YouTube channel. And that does go into base plate design. I won't be looking at base plate design today, mainly looking at the anchors. So we had desktop tools for both Hilti and RAM, and both Hilti and RAM say now don't use them because they've updated their software, and their software is really only available online. So the answers you're getting in your desktop software for these products, you should ignore and go straight to the online version. So if you do a search for Hilti Profis Engineering, you should come to this website. And if you register, you can get through to their design software. And that does a basic design, quite a detailed design of your anchors in concrete. Similarly, Ramset has got iExpert, so don't use the desktop tool, use this online. And again, you can find out the capacity of your anchors in concrete using their little tool. There are some guidance on the Hilti. There's a lot more guidance on Hilti than there are on the Ramset, but I think the Ramset version, although more limited, is far more intuitive. Other tools are available, other fixings are available, but these are two of the ones we use. So here's our spreadsheet, and you'll notice it's under concrete fixings, and we've got Ramset and Hilti. Don't use those sheets. We've got the casting anchors there, and I'd advise you to use this with caution because there may be a couple of errors in it. Let me know in the chat. So a word on failure mechanisms. So it's not just about the steel, it's about the concrete as well and the interaction between the two. So our bolts or anchors are going to be loaded either in tension or shear. And the simplest way is the material failure of the steel, so option 1, or a material failure in the concrete, and it fails kind of like a concrete cone of an individual anchor. Or there's a combination of the two, and more rarely splitting. If you're looking at shear failures, again, the steel could shear. The concrete could pry out, that's tipping it over, or if you're near an edge, the edge or the face could break out too, or there's a combination of the two. Looking at some photographs from testing that some manufacturers have done, and you'll see a failure in tension here, and it's pretty much a cone, and you'll also notice that this concrete is not reinforced, and it's also got relatively small aggregate. But that demonstrates the purpose of this is relying on the concrete strength alone. Tension failures, well, we can also have the steel failing, we can have the anchor pulling out, so that's a failure of the bond between the steel and the concrete, and more rarely a splitting of your member. Shear failures, again, you could fail the steel in shear, which is fairly rare, but is possible. More likely is the concrete edge failure. If you're near the edge, this is where your edge distances become quite important. The whole side of the foundation or the member breaks off. Now, normally the steel isn't the weak link, but if you do something like this, it might well be. This is steel failure with the lever arm. If you have a connection like this, I recommend you don't have a connection like this, because if you put shear into a connection like this, you're going to put bending in the bolts or the anchors, and bolts and anchors do not have a very high bending capacity. So what's the procedure? Well, you first check the anchor bolts. That's the steel capacity in tension, shear, and combined actions. Then you look at the concrete capacity in tension for breakout, pull-out, and blowout. And then you look at the concrete capacity in shear. So that's usually breakout strength as well as pry-out strength. And then you look at the interaction between tension and shear as well. So this is what the standard gives you, and this is the picture of a single anchor and the theoretical failure area. Now, it is theoretical, not practical. Now, if you notice that a single anchor will pull out as failure as a cone, what the diagram shows you is an inverted pyramid. Now, they've used an angle of 35 degrees and you've got no edge issues, so your dimensions are very large to your edges. Other countries use a different failure surface and also a different failure angle. 35 degrees is relatively generous for us, but there are other conservatisms built into the code. And it makes more sense when you combine the anchors. It's quite rare to use an anchor on its own. You'll have 2 or 4 or more anchors. And in that case, your failure surface does look a bit more like a pyramid than a cone. And in shear, the calculations are given for shear breakout with a diagram in the code which shows you how to derive that failure zone, with lots of different diagrams showing for 1 or 2 or more bolts. So here is the Mathcad. Let's open the Mathcad file. So here is the Mathcad for the design of anchors cast into concrete. In this case, it's an edge column, so we've got limited distance in one direction. So your base plate is relatively close to the edge of your concrete foundation. We start with the input. So what loads do we have? And I've taken this straight out of Multiframe and it's gone via Excel. Interesting, if you cut and paste from Excel into Mathcad, it automatically creates a table. A table is just another way of presenting a matrix. So these values here are effectively a matrix. And you then populate the units and the variable value. And from that matrix, you can derive these arrays effectively. So we have strength reduction factors taken straight from the code. We take our design factored vertical load and our design factored horizontal load. So if you want the quick and dirty solution, you just take the worst shear with the worst tension. And if it works, you're good to go. But that can be quite conservative, and we'll see a bit later. So we derive what the maximum tension is in the bolt and what maximum shear is in the bolt by sharing it among the lot. And we've chosen 20mm anchors, and we're going to use grade 4.6. Now, as I've mentioned before, the steel strength is not usually the weakest link in the design of your base plate or your holding down bolts. And so it makes sense to use the lower grade 4.6 rather than the higher grade. Your higher grade is not giving you any more strength. The other aspect is with cast-in bolts, then they tend to get abused on site, and the grade 4.6 is more amenable to being reshaped and rebent. So we have a tensile strength of the anchor group. This is just the steel of 500 and a shear strength of 301 kilonewtons. So the steel isn't being pushed that hard, so our utilization is only 16% in tension and 27% in shear. Our combined utilization is less than 1.2, so we're good to go. Now the more complicated stuff and probably the weak link. Now I say it's the weak link. Now if you think about seismic design, you'd be preferring a ductile failure, and your concrete failures are not ductile. Your steel failures, particularly a tensile steel failure, is ductile. So let's check the concrete under tension. We have chosen a thickness of foundation of 300 millimeters and a concrete strength of 30 MPa. Now, strength reduction factor comes from the code as 0.65, and we're putting a plate underneath the end of the bolt, under the head of the bolt, as 30 by 30. It's a square plate. We're not eccentric, so we can go relatively simple in our design. We put in our bolt spacing and our edge spacing. So our spacing in one direction is 180 millimeters, and in the other it's 230. For the edge distances, we've got 235 and 500 respectively. That gives us an edge distance, a minimum edge distance of 235, our C min, and then we do some magic with the ratios to come out with the formula. So if you look at the projected area of the bolt group, there is a formula given in clause 17.5.72 for the projected area of a bolt group, and we compare that with the projected area for a single bolt group. And we then derive our modification factors. So there's a whole load of modification factors given in the code from equation 17.8 onwards. So there's phi 1, which works out as 1, phi 2 works out as 0.994. Phi 3, now we're assuming cracked in service, so phi 3 is 1. We have a fiddle factor of K equal to 10 because there's a cast-in anchor, and a lambda of 1 because we're using normal weight concrete. These will change if any of the assumptions change. From that, we can derive a basic concrete strength of 110 kilonewtons. If our embedment was greater than 280 millimeters, then we use the second value for the concrete basic strength, which gives us, if we add all those numbers together or multiply all those numbers together, we get a design breakout strength for the whole group as 144 kilonewtons. So our utilization is a little bit higher at 42%. Then we look at the tension pull-out strength of the anchors. We're assuming a bearing area under that plate. So remember, we assumed a 30 by 30 plate under the bolt head. Now, our spreadsheet uses the full area and just says it's the d squared, whereas I've always deducted the area of the bolt itself to be a little bit more conservative. Tell me which one you think is correct. Answers in the chat, please. But that gives you a pull-out strength of 216 and therefore a design pull-out of 140. So again, it's not particularly critical because it's a utilization of 11% in this case. Now we check on the blowout strength. Again, we're still in tension. And again, we've taken our bearing under the plate. And we have modification factors for our edge distances. Here, K1 works out as 0.782, which gives us a design blowout strength of 261 kilonewtons. Again, a relatively small utilization. So now we're looking at shear, and back to those diagrams given in the code. We work out what the shear failure area is. So pull down our applied loads. We've got a perpendicular load in shear of 47 and a parallel of 22. We're not eccentric, and our K2 factor is 0.6. We've pulled down our edge distances and our spacing of our bolts, and a reminder of our C min is 235. So we've chosen a 160 embedment bolt diameter. Now, there is a maximum load-bearing length of the anchor limited by the code as 8 diameters, which may mean you need a larger bolt than you would otherwise assume. This gives us a concrete breakout strength in shear of 80 kilonewtons. And then we have modification factors, phi 5, phi 6, and phi 7. And again, we're assuming it's cracked in service, but we've got additional reinforcement. If you've got no reinforcement extra, then it goes to 1.4. This allows us to derive our projected failure area and the width of the shear face. BV works out as 935 millimeters. Again, we work out our projected failure area for the group and derive the concrete breakout strength for a single anchor perpendicular to the connection. In this case, our design capacity is 66 kilonewtons, whereas for parallel, it's 132 kilonewtons. Now we look at concrete pry-out of the anchor in shear, and we derive a pry-out strength of 289, and that's well within the utilization requirement. So from all of the above, we can work out that our minimum strength of the anchors in tension is 140 kilonewtons, and our minimum strength in shear is 66. All good so far, but then we start combining. And if you combine the worst cases of tension and shear, you'll probably find your connection fails. So this is where I have split my results. So each of these rows represents a different load case. So you'll see our maximum shear doesn't occur with our maximum tension. So we've derived these arrays from our matrix, which was basically the table above, to give us our Rx, Ry, and Rz. And remember, multi-frame talks about linear forces in terms of Rx, Ry, and Rz. In our case, Ry is upwards, and for these load cases, everything's in tension, because when you were designing that anchor, we're really looking at the tension cases. So we can derive what the applied tension is and the applied shear by taking the vector sum and then doing a utilization check. Now it's over 1, but it's okay because it's below 1.2. Equation 17.5 allows you that margin. And here's a summary and a diagram to show you what's been going on. So that was the Mathcad for the design of the anchors. And mention of the references. And yes, that's the concrete code and the ETAG 001 and our technical report from EOTA, technical report 45, both of which have kind of been superseded by Eurocode 2. It's also worth looking at John Scarry's article in the CSOP journal from a few years ago too. So I'll pause there for questions. So we have a question on the difference between category C1 and C2 anchors, and this is all to do with post-installed anchors. And our code, NZS 3101, points to EOTA, technical report 45, and that's where the C1 and C2 categories come from. And because it's Europe, the earthquakes are not quite as big as they are in New Zealand. So they have very low, low, and slightly bigger than low earthquake categories, so seismic activities. And anything bigger than 0.1 is considered larger in Europe. Whereas in New Zealand, that would be considered quite a low earthquake. So you get seismic accelerations of 0.1 G at the north end of Northland. Anywhere south of that, you're probably much bigger than 0.1 G. So pretty much everywhere in New Zealand needs to be designed as a post-installed anchor in terms of C1 and C2. If it's an important class 1, then you can use C1. Everything else is C2. So what's the difference? Well, it's how you test them. So the results you get, the design values you get in the brochures for Hilti, Ramsat, and so on, these manufacturers have tested their product, and the first round is done by static testing. And in a static testing, you wouldn't expect cracks bigger than about 0.3. But to go for earthquake qualification or seismic qualified anchors, you need to do C1 and C2 tests. And you start with the C1 test, which is looking at a 0.5 millimeter crack width, and then you do pulsating tension tests and alternating shear tests. Okay, so far. But once you've done that, you can move on to slightly more complicated things. Here is category C2. And you end up doing a test at a 0.8 millimeter crack. And in addition to the pulsating tension tests and the alternating shear tests, you also do this opening and closing of the crack. This is quite an extreme test, I would think. And the figure for 0.8 is, there's no real scientific basis for that. It just seems like a nice number to use. Here is something that Hilti prepared. So this is courtesy of Philip Grosser at Hilti in Europe. And this is how they do their testing for C2 anchors. So once they've opened a hairline crack and they've drilled in the crack and put in the anchor, install the anchor, they attach a constant tension load and then start recording the loading they're getting. Once they can take it up to 0.5, they can then increase it to get to a 0.8 crack width by increasing the load. And the cycles go on until the anchor either fails or the test ends. And from that, they can derive the residual capacity for your anchor and draw the graph. And so you'll notice your C2 capacity is significantly less than your static capacity. And this is the complaint, that the C2 values you're given, most of your anchors don't work for what we want to do. But hey ho. Which does beg the question, is it cracked or is it not cracked? And in New Zealand, we're finding that engineers tend towards conservatism. And you just assume that it's cracked, unless you can prove it's always going to be in compression. Our code isn't much help either. It gives section 17.5.2, and you can assume it's uncracked if it's not going to crack under normal design scenarios. So what does that mean? Well, for most of our concrete design, you're doing concrete design based on cracked section properties. And somebody's mentioned you also need to consider shrinkage in slabs or shrinkage potentially in beams and walls. So you can't really control whether cracking occurs. So to be safe, assume it's cracked. Unless you can prove that your concrete will remain uncracked for its life, the default to assuming it's cracked is therefore conservative and safe for it post-installed anchors. If you can demonstrate it's uncracked, well, maybe in pre-stressed members. And you want to be careful about installing post-fixed anchors in pre-stressed members because you don't want to hit any tendons. The other alternative is gravity columns with permanent axial load. So if your column or your foundation is permanently under a lot of axial load, then it's likely to be in compression and uncracked. But you need to demonstrate that. So it's usually easier and generally quicker just to assume it's cracked, but be surprised if your anchors don't work. And I think it's quite conservative for column bases under static load. There's a chap from Python called Robert who did a presentation to the Auckland Structural Group, I think it was last year or the year before, and that's available on YouTube, and he goes into much more detail about what is C2 and C1 capacity, because all of these C1, C2 capacities have been aimed at anchors in beams, not really foundations, and he points out what's a beam and what's not a beam. And so by extrapolating on the design of anchors in beams, you might be a little bit over conservative in foundations. Okay, so I haven't arranged next one, and if there's any requirement for a seminar, let me know what topics you'd like me to cover.